January 2026, just the date. If you can see that, then at least the online audience is in good shape. And I'm taking it off so I can see. Okay, great. So they were good online. I just stopped sharing it for a moment so I can see the chat. Okay, we're back to full screen. This is hopefully what the in-person folks will also see.
Yes. Yes, we are seeing it.
Okay, great. I think so.
Go
I
ahead.
think unless somebody says otherwise in the chat, seems like in-person and online can both hear me and see the slides. Okay, I will proceed unless somebody tells me otherwise. Well, thanks for bearing with me and us with the technical difficulties. I had been called for jury duty today, but ultimately didn't have to show up in person. So I'm grateful to be able to be live for both the in-person and virtual audience, despite the fact that I'm not there in person. Better than a recording, I think, any day. So I did want to talk about, of course, uh, the changes in climate, not just that are projected for the near-term future, but also the ones we've already seen, because we are a quarter of the way through the 21st century now and are, in a sense, living in the future that had once been predicted, which, if you think about it, is kind of a remarkable thing to be sort of in the midst of a development that was once a projection of something that probably would happen decades in the future and has now come to pass. And I do, as a person whose job it is to, in some form, divine what's going to happen next, to predict the future, I do often reflect on the fact that, uh, while it's not perfect by any means, I'm hard pressed to think of another branch of predictive science and modeling that has actually pretty consistently gotten the big picture right on what's happening next. So, just in a little bit of a philosophical frame of mind this morning. But without further ado, let me get to the more important stuff, which is okay. So, what's actually going on out there and up there, both figuratively and literally in the case of the atmosphere? Where are we now in terms of the big picture globally in terms of warming? Well, of course, temperatures are rising, the Earth is warming, but really what I want to emphasize in this presentation is that those changes go well beyond the Earth's average temperature and actually beyond, well beyond temperature as a physical variable to begin with. And this is something that we often sometimes forget in talking about these big global, these round numbers that don't sound very significant in and of themselves, 1.5 degrees Celsius of global warming, or 2 or 3 degrees of global warming. What does that actually mean in practice in specific places where humans actually live and where ecosystems actually exist? Well, the reason for the warming that we've seen, of course, is due to the increasing accumulation of heat-trapping greenhouse gases in the atmosphere. That is essentially the entire reason why we've observed this now quite considerable amount of warming. And I just updated this plot, by the way. This is fresh off the presses from NASA just last week, up through and including the end of December 2025. So this is the most up-to-date global warming map you could possibly get, and it's even more red and orange than it was last year, meaning that the warming, of course, is even greater than it once was even 5 or 10 years ago. And there's a few things on the map that are interesting that, since I want to zoom in on California and the time we've got today, I won't focus on too much. But the main thing, I think, if you're looking at this map and you see that it's not the same amount of warming everywhere. There are some places that are warming more than others. And in general, it's the continents warming faster than the oceans, and also the Arctic warming faster than anywhere else. And what this means is the global mean, the global average warming that we hear about, those 1.5, 2 degrees Celsius, for example, those apply not to any particular place where very many people live, because the global mean includes the 70% of the Earth that is oceans, where the warming has been slower. So if we're talking about virtually any point on land, including the United States and including California, the rate of warming is quite a bit faster than the global average. So we are on a multi-year basis, which is kind of the apples to apples, like to like comparison to all of these numbers we hear about in the news and the IPCC reports every few years. Um, we're right around 1.4 degrees Celsius of global average warming as of the 10-year average. But 2023 and 2024, as you may have also heard about in the news, were record warm. We had a couple of years that did reach or even exceed 1.5 degrees Celsius, or about 3 degrees Fahrenheit of global mean warming. So the rate of warming recently has picked up a bit globally. And we do hear a lot about the green energy revolution and all the progress we've made there, which is very real. But ultimately, the number that needs to change is the total top line amount of heat trapping greenhouse gases in the atmosphere. And that number continues to increase year on year. So we haven't yet bent that critical part of the carbon curve. And we're currently on a path towards something like 2.5 to 3 degrees Celsius of global mean warming. So essentially on path to about double what we've seen so far, even with that progress we've seen in emissions and green energy thus far in the last couple of decades. So that is a genuinely concerning amount of additional warming. And as I mentioned, all land areas, including California, are warming faster than the global average, in some cases about double the global average. So you can take these numbers for the global average and potentially multiply them by 1.5 or 2 and get an estimate of how much warmer California could be closer to the end of the current century. So there's some big uncertainty bars in that. It depends both on what we do as a society in terms of our carbon emissions, and it also depends a fair bit on whether we get lucky or unlucky with the unknown unknowns of the Earth's global carbon cycle. But that's just a sort of a ballpark estimate of where we're still headed. And I bring it up in this context mainly to emphasize that we really should be planning for a significant amount of additional warming in California, and that the effects of the additional warming that are likely yet to come will be probably more significant than the warming we've seen so far. But as I'll argue in a moment, those effects have already been quite significant. So, in other words, we really need to be not only addressing the underlying problem of global warming by bringing emissions down as quickly as possible and eventually to near zero, but we also need to be thinking about what we can do in California to adapt to the changes that have already occurred and the further changes we know are on the near-term horizon. So we can and must do both of those things, mitigation and adaptation. So thinking about more locally in California and actually zooming in all the way to Ventura County. Again, this is a plot that I pulled off the NOAA servers just last week. So this is up to date, hot off the presses, including 2025 data. Doesn't really change the big picture, of course, but it adds another data point at the end of this strong warming trend that we've seen since the late 1800s. Ventura County, all of the warmest years on record have occurred in the last decade, essentially. And that's consistent with what we see throughout California. We do see faster warming inland and at higher elevations versus the coast in most of the state, although that's locally not so true along the Central Coast. There has been a really high rate of warming along the Central Coast in particular. We really do focus on this post-2010 era as a bit of a step up. So even though the last few years have been cooler in absolute terms than the peak warmth so far that occurred around 2015, 2016 along the Central Coast, even these relatively cooler recent years would have been historically warm by the standards of the 20th century. So we really haven't seen any cool years in the centennial context in the last decade or so at all. And in Ventura County, turns out to be one of the fastest warming counties in the entire United States. And this has really been sort of accelerated in recent years by this warming spike around 2015, 2016. But again, we haven't really dipped back down to levels we were at prior to that. And so we have the result of that is Ventura County is really a hot spot not only in California, but really throughout all of North America as well. Those were average temperatures, but if we look at peak summer temperatures in the state of California, they're actually warming at an even faster rate. So summer heat waves, especially inland, are well longer and hotter than they were in the 20th century. And along the Central Coast, when sometimes it takes a little bit later in the year to get those heat waves, this is true of autumn heat waves along the actual coastline here. Notably, all of California's hottest summers on record have occurred in the past decade, and as of believe it or not, 2024 edged out 2023 or 2022, I believe it was, for the hottest summer on record, even though it wasn't necessarily that hot along the Central Coast. Inland areas were really roasting, and it's a pattern we've seen often in recent years when some of the hottest years or summers on a statewide basis haven't been the hottest years along the coast. We can talk about this a bit if we have some time for questions at the end, but this year that pattern might be a bit different with some indications of a rapidly developing El Nino event potentially occurring later this spring into early summer. This might be a much warmer spring and early summer along the Central Coast than we've seen in quite a while. And as I mentioned from the global map, the further warming moving forward might occur at about double the rate of the global average in this part of the world. But as I mentioned, arguably some of the most significant effects from a practical perspective of that warming are actually on atmospheric variables and their downstream effects that go beyond temperature. And that's where I want to introduce the notion of the expanding atmospheric sponge effect, which is an analogy, hopefully a visual one that's relatively easy to understand, that my colleagues and I coined to sort of describe the fact that the warmer atmosphere brings about greater variability in hydroclimate. So, in other words, in wet and dry conditions, as the figurative atmospheric sponge, it literally expands with warming. And the way this works is that essentially as temperatures rise, air itself becomes, if you will, spongier. It has a greater capacity to absorb water vapor and also a greater capacity to release condensed water in the form of precipitation. But it doesn't do so all the time. Of course, most of the time in California, it's not actively raining. And so more often than not, the air is in fact spongier and drier than it would normally be, but when it is precipitating, the potential for heavy downpours increases. And I think we've really seen that in Southern California quite dramatically over the past couple of years as we've swung rapidly back and forth between near record or even record wet along the Central Coast conditions, including this year so far, and record dry in between, as we saw before the LA fires. And I'll talk a little bit more about that later. But what this means in practice is that there is, by virtue of this expanding atmospheric sponge, an increased ceiling on how intense precipitation can become, but also on how intense evaporation can become. So you can already kind of get a sense of how this might be driving larger swings between extreme wet and extreme dry as the figurative sponge expands. So in practice, this means potentially heavier downpours, but also a greater atmospheric thirst and greater dryness when it isn't raining. And so the net result is what we term increasing hydroclimate whiplash. And this is something that is not localized to California, although we certainly see it here, but is actually something that we expect to be true virtually everywhere on Earth, except for a couple of remote subtropical ocean regions where almost nobody lives. So this is likely to be a truism almost as much as warming temperatures themselves, which is that the swings between the wettest wets and the driest dries will increase rapidly and, like temperatures, faster over land than over oceans. And this is something that we expect to accelerate between about 1 and 3 degrees Celsius of global warming. And remember, where I pointed out that we were in one of my first slides, we're right in the middle of that range right now, right around 1.4 degrees Celsius. So this is something that we really expect to be taking off in the range of warming that we're going to be experiencing for much of the rest of our lives. So I think the motivation for why we should care about this particular aspect of climate change is maybe especially obvious to Californians and maybe even more obvious to folks who live in Southern California and the Central Coast, given recent events. But I do think it's worth emphasizing. This was a slide by the way, I created back in 2018 when the Thomas Fire, which, if you recall, burned in December of that year, became the largest fire in modern California history in December. It's since been eclipsed multiple times by larger fires since that date, which is also hard to believe. But if you'll recall, it was immediately followed in January 2018 by one of the worst flash flood and debris flow events in modern history as well in Santa Barbara County, particularly in and around Montecito, with a really deadly and destructive mud flow event when a really heavy localized downpour fell right on the wildfire burn area just a couple of weeks after it occurred. The reason I use this as a pretty stark example of why we need to be understanding the variability or the volatility or the whiplash in California hydroclimate is that if you take the statistical average during this period, the climatological mean, if you will, well, you might say it was on average mostly sunny and a bit breezy with below average precipitation over this 2 month period, which of course really doesn't describe any of the high consequence conditions that unfolded during that period. So often, if we consider changes in average climate, then we're often going to miss the point entirely. And this may seem obvious, but when I see folks applying climate change data and information to any number of practical applications, that's often exactly how it is done. And so we're going to, if we do that, do so at the risk of missing the very kinds of high impact events that are the most disruptive, that we're probably most motivated to try and understand and mitigate the risks associated with them. So, okay, so what else is going on in California? Well, uh, we haven't really had a strong trend in annual average precipitation. In fact, if I included the most recent year of data, this is 1 year out of date, this would be even more muted. It's essentially a perfect horizontal line over the past century. So no significant trend in long-term average statewide precipitation. And yet we do see an increase in the variability of moisture conditions. So if you aggregate temperature effects, the evaporation, and precipitation, we actually do see that we're wiggling around, we're oscillating around quite a bit more at the end of this time series than we are for the average precipitation. And yet this is occurring in the same period where we have seen objectively a large, statistically significant, physically robust, whatever you want to call it, increase in drought frequency and severity. So all of these three things, by the way, are using the same data. So we see a strong increase in drought frequency and severity, no meaningful decrease in average precipitation, but a large increase in hydroclimate variability. So I think this helps to start to illustrate what we're talking about here. Whereas if we were only trying to infer what's going on here from changes in average precipitation, we're also not going to get a clear picture of how things are actually unfolding. So California, of course, already had a highly variable hydroclimate. The fact that the year-to-year and seasonal variability in this part of the world is quite high is not in itself something new. And this has been true by virtue of the geography and climatology of the region that we're in. And that's partly because we exist inherently at a bit of a boundary zone in a global climate sense between a more active mid-latitude region to the north, think the Pacific Northwest, and the quieter subtropics to the south, think northern Mexico. And for this reason, we ultimately have a really strong seasonal cycle. So wet winter, dry summer, pretty definitively in most years, except for a couple of really weird years recently, which you may remember. We also have a really strong latitudinal gradient. As you know, it's much, much wetter up in the rainforests of northwestern California, up by Eureka, Arcata, than it is, say, in downtown LA or San Diego. This all lends itself to really high variability year to year. We're on the margin of the Pacific storm track, and the fact that we really only see meaningful precipitation in most of the state during the winter time means that if we miss out on any given winter of precipitation, we're more or less out of luck until the next winter. Unlike other parts of the country, we don't have the ability to we don't really have the ability to make up that gap at other times of year. So we have to wait a whole seasonal cycle and hope that the following winter is wet. And if that winter too is not wet, well, now we're in a pretty serious drought, as we've seen multiple times in the past 10 to 15 years. So this is a slide from a paper that now feels old in the context of modern climate science back all the way back in 2018. Of course, it's not really that old, but it feels like it, since it feels like a world away. But the basic tenets here, I think, still apply. When we look at climate model projections for the future for a much warmer California, what we actually find is that that relatively little change in average precipitation persists moving forward. So we still don't see a really big increase or really big decrease in California average precipitation. Maybe a little increase in the north and a little decrease in the south, but not very large compared to the already really high variability from year to year that we already experience. But those very same climate models indicate a profound increase in both the wettest wets and also the driest dry. So this is not to say that some models are wetter, some models are drier, and some don't have much change. This is to say that on average, almost all of the models don't show a big change in the annual average precipitation, but almost all of them also show the very same models, the very same predictive models using physics and chemistry suggest that the variability of that precipitation from year to year and within seasons is going to increase. So essentially, what it's telling us is that the average is masking, if we only look at the average, the increase in variability that we're likely to be experiencing on the ground. So that's a really key point I just want to keep hammering home because I think Southern Californians are living it right now, but we still sometimes, when we think about climate change, ask about changes in averages. And when it comes to the hydroclimate and precipitation and drought and wildfire, that isn't going to cut it. So as I mentioned, muted changes in overall average, maybe a little bit of an increase in the north, maybe a little bit of a decrease in the south, but the bigger picture is that the variability increases by a lot in these projections, not just from year to year, so from one year to the next, but also within seasons. So if we're talking about variation from one month to another month within the rainy season, so from November to December to January to February, for example, increased swings between wet and dry there too. And I think this winter currently is a great example of that, with much of Southern California having had a near record wet start to the rainy season due to extremely wet conditions early in the season in October and then again in December with significant flooding in some areas, but also really, really dry months in between. It hasn't rained now in weeks again in Southern California. And it's sort of spring or summer like warmth once again. So we're kind of living this prediction again in this very winter. Um, we see this too with the seasonal cycle as well. With an increase, we already have, of course, a pronounced wet winter, dry summer seasonality in California, and we expect that to become on average, even more pronounced with, on average, drier autumns and springs, but maybe slightly wetter winters. Again, sort of making the annual average precipitation metric a little bit misleading. And of course, this really matters a lot in terms of having really dry autumns that coincide with strong wind conditions or even early winters in a really late onset year. From a wildfire perspective, we of course saw that last year in Southern California and in prior years in Northern California. But it also matters a lot for agriculture because it means that you have a longer growing season on the one hand, but you also have a longer water deficit or irrigation need season. So you have more days per year and a longer sequence of consecutive calendar months where the natural atmosphere is not providing the rain that you might need directly to your crops, and it means that you would have to apply irrigation water for a longer period on average, even with relatively little change in the average annual precipitation. It also means that you're more likely to get swamped during the winter with more water than you'd actually want on those fields. And, that affects water supply writ large. It affects wildfire risk, agriculture, and of course, the wildlands of California because we don't have any irrigation of our forests and our grasslands and our chaparral, of course, unlike for cultivated agriculture and farm fields. So where is all that extra water coming from in those more intense bursts? Well, it's probably going to be a familiar delivery mechanism, but an intensified version of it. These are still mostly going to be wintertime atmospheric river storms, which is how most of California's water is delivered in the historical climate as well. But we expect these to become significantly moister and significantly stronger and capable of dropping, at least sometimes, unprecedented levels of precipitation. And we've actually seen a number of instances of record-breaking short-duration precipitation in Southern California in recent years. Think of some of the extreme downpours we've had in Oxnard, for example, with that localized, really intense flash flooding. Think about the downpour that in 2018 that caused the debris flows in Montecito. The Central Coast has actually seen quite a bit of these examples of these increasingly intense heavy downpours in recent years, even in the same period where some of the worst wildfires on record have occurred, as well as the worst droughts. So, my point, just to emphasize, is these are not mutually exclusive things. They can happen in the same decade, of course, and sometimes even in the same winter season. Previous or more recent research, I suppose, 2022 isn't quite as far away as 2018 was. We find that the likelihood of a really severe statewide flood event has probably already increased quietly in the background. We published this immediately following some of the worst droughts on record when I think there was more skepticism since 2022. Of course, 2023 was extremely wet in Northern California with significant flooding, and then Southern California has been really wet the last couple of years, at least at times. And so I think maybe the level of skepticism of this kind of claim that we're already sort of living in this era of increased flood risk is maybe it's a bit of an easier sell with some of the really heavy downpours and floods we've seen recently. But I think the key here is that with each increment of warming, this risk is going to continue to rise. And if we do make it up to 1.5 to 2.5 degrees Celsius of global warming, which are the numbers you see here along the horizontal x-axis, the likelihood of a really severe statewide flood event goes up rather dramatically to the point where it's something that most of us statistically probably would not have experienced in our actuarial lifetime. So, in our 70 to 90 year optimistically lifespan, there's a good chance that we wouldn't have experienced one. Whereas in a 1.5 or 2 degree warmer world, which is a world that we will all likely live in sooner rather than later, the odds go up to being something that we probably will experience within our lifetime. And so that really pushes us over the edge in terms of sort of maybe being able to hope that we don't have to deal with something like this to something that becomes a much more plausible target for adaptation because it's more likely than not something that we will need to deal with in our lifetime and perhaps sooner rather than later as temperatures warm because the cumulative risk of a severe statewide flood event between 2020 and 2060, so sort of roughly the next 40 years, I guess that's a little bit less than 40 years at this point, is about 2 and 3. So more likely than not, this is something that most of us will still be around to experience. And so we should really be thinking about ways to mitigate those risks. On the dry side of that expanding atmospheric sponge, again, the same picture kind of emerges if you look at the broader Southwest. This is true of the Colorado River Basin as well, where these plots on the left come from, where there's not really much of a trend in average precipitation so much as there is a really strong warming trend and a large increase in drought frequency and severity. So really what this is telling us is that the same amount of rain and snow just doesn't go as far as it used to. We've got more precipitation falling on fewer days per year with maybe more intense but fewer individual storms. Snowpack in the Southwest is a big part of this, and we're living through a winter where not so much in the central and southern Sierra, where snowpack is doing all right this year, but in the interior West Colorado River Basin, both upper and lower Colorado, record low snowpack at currently out there due to this record warm winter out there. That means that the soils are drier, and combine that with greater atmospheric evaporative demand, well, droughts in the 20th century, you could get warm droughts, you could get cold droughts, but now they're just all hot droughts because it's warmer than average all the time now. You can blame the dry side of the expanding atmospheric sponge for this one. So just to emphasize that a lot of what I'm talking about here is specific to California, and even the Central Coast is maybe a bit of an epicenter, but it's also far from isolated to California, and this is part of the bigger picture of how we should be thinking about it. So I'm going to skip through this just so I have some time for questions at the end, because I did want to get to the wildfire piece of this. And what we know globally is that from a meteorological perspective and from a vegetation moisture perspective, uh, wildfire risk is increasing almost in almost all of the Earth's fire-prone regions. There are very few, if any, places where wildfire risk is decreasing. And this is not a statement about how forests are changing or vegetation management or policy decisions or anything else. This is isolating the question to just how has the weather changed? How has vegetation dryness changed in a way that would influence wildfire activity? And the answer is everywhere where there's a change, it's an increase. And in some cases, like California and the western US, it's a large increase. And this is mainly, again, due to the dry side of that globally expanding atmospheric sponge, driving decreased humidity and increasing evaporative demand. So essentially, even if we're not seeing decreases in precipitation locally, we're seeing drier vegetation because when it's not raining, that thirstier atmosphere is drawing more and more moisture out of vegetation. And of course, the same argument would apply in an agricultural context. The main difference with agriculture is that hopefully you have irrigation water in most cases that you can actively apply to compensate for that thirstier atmosphere. You start to run into some problems, of course, during a severe drought when there might be water supply restrictions, which we do not have right now in California. But again, in the natural landscape where there's no irrigation water to apply, this gap is a real gap that you can't really compensate for. Whereas if you're growing strawberries, say, in a farm field, you potentially can apply more water to offset the increasing atmospheric demand. So you have more levers that you can pull when you're actively cultivating crops than you do on natural landscapes, which of course is where wildfires are occurring. And just to emphasize, we do find this is true in California. The increase has been particularly pronounced in autumn, but it's not just autumn that's relevant. And I did want to walk through briefly sort of what happened. I know we're just past the 1 year anniversary for many of these for the devastating wildfires, especially the Eaton and Palisades fires in LA County that occurred last January. But I just wanted to remind folks the sequence of events that led up to that, because we're all familiar about how it was extremely dry and also very warm with no onset of seasonal precipitation all the way through January, late 2024 into early 2025. But remember what happened just before that? Winter 2023 and 2024 in LA County and also all of the Central Coast, including Ventura County, was extremely wet. Everything was very lush and green. There were some significant flooding issues that winter. And so in spring 2024 into early summer, we were sitting pretty in terms of water. The vegetation was really green. There was a nice wildflower bloom out there in the desert as well. So we had a lot of growth. It was probably a very good growing season as well for many field crops for the same reason. There was a mix of wet enough soils, but enough sunlight and warm enough temperatures to do a lot of growing. Well, that also happened in California's wildlands and Southern California grasslands and chaparral settings in particular. There was a lot of additional growth of herbaceous biomass, so the grass fuel loading, as you might call it. There was about twice the usual biomass of herbaceous vegetation in Southern California come June and July 2024. Then across California's inland areas, not so much again along the coast where it was not that hot of a summer, but once you got above the marine layer or east of the mountains, it was literally the hottest summer on record in Southern California inland areas. We then got to a fall where even September had record-breaking heat even at the coast. If you remember that September 2024 heat wave in LA and Ventura counties and the wildfires that broke out then, which at the time were pretty destructive in their own right. But then it didn't rain all autumn into the early winter, and we had record-breaking atmospheric thirstiness. So envision a record-sized atmospheric sponge that autumn into early winter. So what we did is we had that vegetation accumulation cycle and then an extreme and even record-breaking vegetation desiccation cycle on December 2024. September through December 2024 were again it was essentially the driest such period on record for coastal Southern California, and this led ultimately to a really volatile combination of highly abundant grasses and fine fuels, record dry chaparral and brush in the hills above LA. And then when we had a really strong offshore wind event in January, well, we all know what happened next. But I've added one more piece to this slide just for this session here. It's that green arrow going back in the other direction because, of course, as you know, this most recent few months, from about October 2025 through the present, is one of the wettest starts to the rainy season on record in Southern California. And I just want to emphasize how extraordinary that sequence is. From the second wettest 2 year period on record, ending in spring 2024, to the driest 3 to 6 month period on record, once again, in from about September through January of 2024-2025, which led up to these fires. And we're right back to that extremely wet, highly favorable vegetation growth period again in late 2025, early 2026. That's quite some whiplash, especially considering that the two worst droughts on record in the very same part of southern and central coast of California occurred between 2010 and 2020. That's a lot to have dealt with over a 10 or 15 year period, and I understand, and I can relate if more than a few of you are a bit exhausted from this. And we do see this, this purple line here is really what in the top plot here, you go from about 1900 through 2024, is the main thing that illustrates that the whiplash, the late season moisture variability in Southern California has in fact increased by about 25%. That is not a small increase, considering it was already pretty high to begin with. This is mainly being driven by a large increase in the driest dries, more than a large increase in the wettest wets. But importantly, the wettest wets have not gotten any less wet in coastal Southern California. They're just as wet as they've always been, but we're expanding the distribution on the dry side. So if the wettest wets stay the same, the driest dries get a lot drier, the gap between them essentially is widening. And this then becomes really important for, you could call it off-season fire risk. It's not really off-season because we do have occasionally really dry vegetation and also very strong winds in winter. But if we just look at the November through January period, which is sort of peak Santa Ana wind season in coastal Southern California, we see that the peak severity of fire weather conditions has increased by an even greater margin, by about 36%, and that's only since 1980. So just essentially over about a 40-year period or so, we actually see that a 40 to 45-year period, large increases in the fire weather conditions during peak wind season. And again, that's mainly because we're seeing drier and drier peaks increasingly overlapping with that Santa Ana wind season. We're not seeing an increase in the Santa Ana winds themselves, but what we've seen is an increase in peak dryness during Santa Ana season, and that is what has driven a lot of these high impact fire events. And there is recent research that has illustrated this. This has been something that ecologists in coastal Southern California have pointed out for a long time, that in the kind of fire regimes that we have in coastal Southern California, which is mainly not forests. You get into forests if you go up in the mountains, of course, but if you're talking about coastal Southern California, where most people live, in the hills and valleys around LA, for example, and in the lower hills in Ventura County, it's mostly grassland, shrubland, and some mixed oak woodland or juniper woodland, but mostly it's not a contiguous dense forest. These are what are known as fuel limited fire regimes, where year to year the amount of grass varies a fair bit based on growing conditions, much as your field crop conditions might vary year to year. And it's following the wet periods where you have the most growth of grass, where that fuel availability is highest. This had long been hypothesized that not only was the wet side important in terms of vegetation growth, but the rapid transition to dry was also required to, as you would expect, dry out all of that increasingly abundant fine fuels, grass fuel potential for fires following those wet periods, but it had never really been conclusively demonstrated. But there's a new paper out this year that indicates really clearly that there is essentially what is known as this moisture cascade, where in coastal Southern California, in the grassland and chaparral regimes, when you're outside of a forest, essentially, the most active and most intense fires actually follow periods of rapid transition from very wet to very dry conditions. So it's not just the very driest conditions that result in the worst fire conditions in coastal Southern California, but rather the strongest whiplash transitions from extreme wet to extreme dry. This is directly related to that potential fuel accumulation then desiccation cycle that I mentioned earlier. And this is exactly what we expect to see more of with increasing hydroclimate whiplash in this part of the world. Arguably, we've been living it these past few years. Now, in forests, it's maybe the more intuitive thing is still true, which is the drier it is, the higher the fire risk. So really, the worse the drought, the worse the fire risk in California's forests. But if you are in coastal Southern California, and I would include most of Ventura County in this, the highest risk is actually going to follow these extreme wet to extreme dry cycles, which are increasing in frequency and magnitude as temperatures increase. And you can blame the expanding atmospheric sponge for that one too. So I just want to sum it all up. Hopefully we'll have a little bit of time for questions. I know we were slightly delayed by some technical issues, but I just want to offer a bit of an overview. We do expect to see increased precipitation intensity and overall aridity from that expanding atmospheric sponge. I didn't talk too much about snowpack in this context because Ventura County is not exactly a bastion of California snowpack, although of course it does sometimes snow in the higher peaks, but we will see less of that, and this winter is an example of that. More extreme heat is maybe the most obvious piece, and increasing wildfire risk for the reasons I just mentioned. Really, the theme here is greater variability, wider swings. The only thing I don't think we're going to see are colder colds. We can probably cross that off our list of concerns since it's just getting warmer. But in terms of hydroclimate, wetter wets and drier dries as it gets warmer are likely going to be the theme. So um, that means, well, that could mean good and bad things. It means that it's going to be more difficult to manage our water. It means that we will see these increased hydroclimate rebound cycles that lead to higher fire risk in coastal Southern California. It also means we're going to have to deal with, yes, more severe droughts and probably more severe floods too. But the other side of that coin is that the fact that we don't necessarily expect to see large decreases in average precipitation means, well, we are still going to get that water. This notion, I think, that California will sort of perpetually shrivel up like a raisin in the sun, as it were, is not necessarily correct. We will see drier dry periods and worse droughts and worse wildfires, and we're already living that. We have to manage that. But the fact that we will still get this water delivered in really big bursts, like this year, is itself maybe slightly less bad news because it means that the water is still going to be there, but we're just going to have to learn to manage it in increasingly inconvenient and in ill-timed bursts. But it is a different problem than the rains not arriving at all. And I think we see that this year where, and even last year with the severe fires in Southern California, those did not occur during a severe multi-year drought. And we did not really have any serious water supply issues last year, despite a record dry period, because we do have a water management infrastructure that gives us that carryover. There were not agricultural concerns from that record dry period so much last year because there was plenty of irrigation water available in most cases because of that robust water management infrastructure. It's really only once we get into those multi-year drought periods where that starts to become a bigger problem. So flexible and proactive interventions are going to be the name of the game. That's going to be the commensurate match for the climate adaptations that are going to work in an increasingly variable hydroclimate. And how do we adapt to that? Well, on the fire side, prescribe fire, thinking more about building fire resilient communities, learning to live with and work with fire rather than fight it so aggressively in all of its forms. And the same thing I think is true of water and flood risk, where Central Coast is a great example of a place where there's been a really big push for river and floodplain restoration. Specifically in Ventura County, even. I visited some of those Nature Conservancy floodplain restoration sites in the last few years, and they're a pretty big success. And hopefully we can build off of those successes to increase not just our flood resilience by reducing our exposure along those riverbanks, but also increasing groundwater recharge and then simultaneously giving us a bit more resilience to the droughts that will come as well. We do need to stress test our infrastructure to the big bad risks of flood and wildfire moving forward. and to future-proof the new projects that we're building, because history, I think it's pretty safe to say, is no longer an adequate guide there. But really, I think one of the big opportunities is to focus, as I mentioned, on resilience, because there are going to be a lot of projects and interventions that are beneficial to both humans and ecosystems, even if the climate were not changing, but become especially beneficial in our current reality where it is. All right, so I just wanted to close with that. Hopefully, it's time for a few questions. As was mentioned, you can find me all over social media. If you're interested, there is a survey through UC ANR. If you'd like to help out with us trying to ascertain who we're reaching with our weather and climate communications activities, there's a QR code on the slide here. You can scan it with a smartphone or another device and take that survey at your leisure. It's pretty short. But with that, I think I'm all done, and hopefully we got time for a few questions. Thank you. I'll wait for someone's cue. I'll leave the slide shared for another minute or two, and then I'll take a look at maybe the Q&A myself. Okay, let me take a look at the Q&A myself as well. So I'm going to stop sharing my screen. You'll see my face back here. Um, let's see here. Just trying to check if there's Q&A in the chat.
So, okay, thank you so much, Daniel, for your very enlightening presentation. We are gonna take some questions. Let's go for about 3 or 4 questions. Are there any questions, first of all, in the room for Daniel? Yes, Ben.
How does this uncertainty affect our 1 week, 1 month, 6 month, 1 year forecast for weather?
Don't know if you were able to hear that, Daniel?
Yes, I was actually. So the question, just for the benefit of folks online, if they weren't able to
Oh,
hear
now
us,
we can't hear Dan.
how does this uncertainty
Okay.
affect
Can you
sort of atmospheric
unmute
predictions on
Dan?
other timescales? So
I'm so
essentially,
sorry.
like daily weather forecasts and sort of seasonal outlooks. That was the question, and it's a good one because
Oh,
they're
Daniel,
not.
did you mute yourself?
No, I think we're back to the same issue before. I suspect the folks online can hear me,
Okay.
but not
Okay, did
the.
you hear Ben's question?
Yes, I did. Can you hear me again?
Okay. Yeah, so if you could please answer that one. We
How
need
does uncertainty affect our 1 week,
Yeah,
one month,
I
six
was able
months,
to hear
one
it.
year
I actually
forecast?
repeated it for the online. I think we still have some audio syncing issue with the in person. But in any case, it's a good question. Essentially, weather prediction and climate prediction, while very related, and actually I tend to think that we've sort of overblown the separation between weather and climate science in some sense, they are still different prediction questions from a process perspective. And so we actually have better weather forecasts today than we ever have in all of human history. We have more reliable weather forecasts circa 2025 than ever before. They continue to improve. They will likely continue to improve moving forward. So the good news is your 3-day, your 5-day, or 7-day weather forecast literally has never been better. Sometimes you got to go to the right sources. There's a whole different conversation about why smartphone weather apps are terrible for a lot of this. But the actual data behind them, the numerical predictions are better than they've ever been. The gray zone challenge when it comes to seasonal predictions, going once you get past a couple of weeks and are looking like a month, multiple months, or even a season or two in the future, or several years in the future, is that we lack meaningful predictability there on those timescales unless there is something kind of unusual going on. Like, for example, if there's a strong El Nino event or something, that is going to give us some predictability, not a slam dunk definite seasonal predictability, but it's going to give us some indication of, say, the precipitation to come in Southern California in a given winter. But a lot of years we don't have those kinds of signals, and even in some years where we have those signals, um, other things outweigh them. Like this fall, for example, we didn't really have a particularly strong signal for for precipitation in either direction in coastal Southern California, and yet it was literally, in some cases, the wettest start to the season on record. You might have thought that would have been something that was at least a little bit foreseeable. And in this case, it wasn't. We did not have strong El Nino conditions. We did not really have any other specific indicators. So it is to say, we have great weather forecasts, and then climate projections are different, on multi-decadal timescales because we don't have to pinpoint what happens in a specific year. We're just talking about the general envelope of weather conditions in the future. And so we can kind of have this better sense of what's happening, ironically, a few decades in the future, and then also on very short timescales of a week or two, but not so much in that gray zone in the middle because you transition from one kind of prediction problem to another. So in general, we're still going to have reliable weather forecasts moving forward. That's the good news. Maybe we'll advance in this predictive gray area as well, but it's always likely going to be the case that, frustratingly, there's going to be this gap between really good weather forecasts and these longer term multi-decadal predictions.
Thank you so much, Daniel. Would you be able to read one question from online? Are there any
Yes.
questions
I can answer a couple quickly. I think there's one question, is data quality an issue in Ventura County due to weather station location? It could be maybe across the more remote inland parts. So once you get up into the mountains and beyond, maybe, but in general, there is enough data to really get a realistic sense of what's going on. And this does not, I think the fact that Ventura County is one of the warmest warming places in the country is not an artifact of the data. It does appear to be real as far as we can tell. And then there's a related question. How did weather conditions during the Thomas Fire compare to the recent LA fires? Were they similar? Well, in a sense, they were similar in that there was a really delayed onset to the rainy season. So it was very dry all the way through December of 2017 along the Central Coast and coastal Southern California. And there was a significant prolonged Santa Ana event. The one in 2017 wasn't quite as strong as the one in 2025, but it was very multi-day prolonged. But I think that just gets us to the point that offshore winds are not rare in December or January in Southern California. In fact, it's the peak of the seasonality. If you had to pick two calendar months when you would expect Santa Ana winds to occur, it would probably be December and January. So that itself is not so rare. What was rare and what was the real problem here and the catalyst was that we had really dry conditions really late in the season. Usually by December or January, even if it hasn't rained a lot, it's rained some. And in both of these years, it essentially hadn't rained at all leading up to it. So what I don't think we had in 2017 to the same extent was really wet conditions the year prior, although I guess 2016, 2017 was a reprieve year from the droughts that preceded it. So in a sense, yes, we had a similar situation, not as extreme of whiplash as we had in 2025, but it's the same general idea where you have unusually dry conditions that persist unusually late into the season, and then you have a relatively normally timed wind event that coincides with abnormal seasonal dryness that really results in at least the potential for very fast moving and destructive fires. So that is sort of this condition we look out for. And this year is a good example of a year where, of course, we did not have that risk because it has been so wet from October and through into December. We have almost no appreciable risk of severe fires right now in Southern California. Even if we have strong wind events, it's just not dry enough, which is the good news for the moment. But you can kind of see how that moisture variability from year to year is really modulating that. We have had offshore wind events this year, but we haven't had consequential fires because the grass is green and there are puddles all around.
Okay, well, thank you so much, Daniel. If there's any additional questions in the chat that you feel you have the ability to answer online, that would be great. I think we have to move on to our next speaker, but I want to thank you so much for this very enlightening talk. Let's express our appreciation.
Thanks again for having me. I'm glad it all worked out in the end.
All right, we'll move on to our